The focus of today's lesson is graphing quadratic functions. In the past, we have graphed linear functions, and the graph of a linear function is simply just a straight line. You're going to see today the difference between a linear function and a quadratic function is mainly in the shape of their graph and the form of their equation. We know that the form of a linear equation is y equals mx plus b. And we've worked a lot with linear functions and their equations. Today starts the in-depth analysis of quadratic functions and their graphs, and we're going to learn today how to plot the points and how to graph these functions and why they are different from linear functions themselves. So a quadratic function is a non-linear graph. The equations take the form y equals ax squared plus bx plus c. Now, f of x, remember this is function notation that we learned quite a while ago. F of x is how it's pronounced, f of x. And f of x and y are the same thing. So you will see these two used interchangeably, and you need to know that they mean the same thing. In your TI Inspire, you will only see f of x, and you will need to know that you need to take a look at the rest of the equation. Again, y and f of x are the same thing. A quadratic function has a graph whose shape is called a parabola. And we're going to see what a parabola looks like in just a second. So these graphs, or these equations, ax squared plus bx plus c, should look relatively familiar. We've been graphing, we haven't been graphing, we've been factoring these polynomials, something like x squared plus 2x plus 1. We've been factoring them, and now we're going to say, well, what if this were a function? How could we graph it? What are the solutions? What does it look like on a graph? And we're going to take a look and analyze that in a different way. So why do we care about quadratic functions and their graphs? Well, you see them everywhere. They're in engineering, they're in architecture. So if you'll notice, I've set up a few pictures where we can see that a parabola is really this curvy U shape. It can be upside down or it can be right side up. It can be sideways, either way. And we're going to throughout this unit, we're going to look at the difference between them, but you'll notice a roller coaster takes the shape of a parabola, the arc of a dolphin jumping out of a water, the arc of a bridge. So again, here it's used a lot in architecture, and that's really important. Again, in this window, you'll see a parabola as well. In the shape of the water that's coming out of the water fountain, that's the shape of a parabola. And so is the arc of this basketball going into the hoop. And you'll notice that once we get to the application of this unit, you'll see a lot of questions involving the height of a ball being thrown, or a ball being hit, or something like that. So what's really nice is that quadratics have such applicable situations, and they help us. It's helpful when we try to connect it to the real world. So when we want to graph a quadratic, we're just going to go into the graphings page. So if you go into your calculator and go to a graphs page, we're going to take a look at this basic quadratic where it's f of x equals x squared. And remember, you're going to hit Control T to look at the table of values once you type in the equation. So what's important is that you really notice this table, and I copied the table from a calculator to show you what it looks like. Here is our x value, and all the x values are down this column. And now you'll see here f1 of x equals x squared. This is basically your y values. So you have your x's and you have your y's. When you graph a quadratic on your own, you want to look for a pattern, a repeating pattern. So if you notice, and this is really going to be in the x's and the y's. If you notice here, my x's are on this side, and they don't entirely matter when we look for this repeating pattern. What we really need to look at is the y values. And if you notice, we have 4, 1, 0, 1, 4. It's kind of like a mirror image of itself, and if you find that pattern, you will really get the shape of the parabola that you're looking for. So if we were to graph these, remember we write a coordinate as 2 comma negative 2 comma 4. So I'm going to go across 2 up 4 and plot my first point. Again, bear with me, this is a little bit of a small graph. Our next point is negative 1, positive 1. Whoops, let's get rid of that. Negative 1, positive 1. So we're going to go across negative 1, up 1. Then I have 0, 0, which is my origin. Then I have 1, 1, which is right here. And then I have across 2, up 4, which is here. And you'll notice already before we even connected that it makes sort of a U or a V shape. Now when you connect these, you must connect them with a curve. We don't want this like V looking shape because that's actually the graph of a different function. So we're going to just connect it with a nice curve, make it look kind of like a U, and put arrows at the end because we're taking points from a table of values and they can extend indefinitely in either direction. And that's how you would graph this, and of course you would label in the end. There you go. Okay, so here is the second graph that we're going to take a look at today. So notice the first one, f of x equals x squared. That is called our parent function. And basically what that means is that every other quadratic is based off of that one. So notice we have f of x equals x squared, again our parent function, but then we're doing some other stuff to it. So again, here's my x value, here is my y value. So I'm going to start plotting. So we have negative 3, 4, so that's all the way across here. Negative 2, 1, negative 1, 0, 0, 1, 1, 4. And again, it makes this U shape because we have this mirrored pattern here, and 0 is kind of the middle of that pattern. And that's what you need to look for if you're scrolling through your own table. And again, we connect with a nice curve, and yours should be much neater than mine. I have this stylus is not entirely accurate, so you want to be careful. And f of x equals x squared plus 2x plus 1. Okay. Okay, here is this last quadratic, and we're actually again going to graph this together just to take a look at what the graphs look like. So again, here is the only difference here now is that we have a negative x squared, and I'd like you to take a minute to think about what that does to the quadratic, to the parabola itself. If something is negative, what do you think that's going to do to the graph? Now remember, if something were y equals mx plus b and the slope were negative, it would start off as positive and then it would go to negative. It would become negative slope. Now in this case, in a parabola, the slope is changing all the time. So first we're decreasing, then we're increasing as we go through the parabola itself. So we're going to take a look and see what happens with this parabola. Again, I'm looking for the repeating pattern, so I have negative 2, 1, 2, 1, negative 2. Notice that right here is that middle point, and that's going to be very important when we start analyzing these graphs. So if we start to analyze them, we take a look. So it's negative 1, negative 2, and at this point you should be graphing all along with me. If you don't know how to graph, you should really go back and review that because that's something you're really going to need here. So across 0, up 1, across 1, up 2, across 2, up 1, and across 3, down 2. I'm just going to fix this guy I've got right here. And that was negative 1, negative 2, which is this guy right here. So if you'll notice, we can connect it with a curve. And you'll notice the shape now is upside down. So this negative 1 really just flips our parabola upside down. And that's really it, is graphing these quadratics and being able to copy points from a table, which I hope that you'll be able to do by the end of this lesson. Have a good one.